All right, so now we want to discuss another way of solving the non-homogeneous differential equations, where the undetermined coefficients or the annihilator method really will not work. And so the next topic is this variation of parameters. Now, the nice thing about variation of parameters is that it's not just tailored straight to differential equations with constant coefficients, those linear differential equations with constant coefficients, where the undetermined coefficients, we need that to happen. So with the undetermined coefficients, the annihilator approach, not only do you have to have it be a non-homogeneous differential equation where that function on the right-hand side is able to be annihilated, but it also, the left-hand side of the equation has to have constant coefficients. Variation of parameters is a little different in that there's very little requirements as to when you can use variation of parameters, so it's much more widely able to be used for a lot of differential equations. The downfall of this variation of parameters is we're going to need some linear algebra. Now, without having a big background in linear algebra, if that's the case for you, we could still get through it. There's something called Cramer's rule, which, if you had linear algebra, you would have learned Cramer's rule. But ultimately, Cramer's rule turns out to be a formula for solving a system of equations. So while you might not know where the formula comes from and why it works, you should still be able to use the formula. Okay? So we can see with first-order linear differential equations, if we're working with a first-order linear differential equations, we can see that we can form a particular solution as U1, Y1, where Y1 is the general solution to the homogeneous, and U1 is this random function. And we could say that a particular solution can be found in this form for a first order. Now, what variation parameters does, it says, well, if that works for a first order non-homogeneous differential equation, then shouldn't we be able to form something similar to that for a second order? All right, and that's really the idea here. So we'll work with a second order differential equation. So when we're working with variation parameters, we're going to work with a second order linear differential equation. It's non-homogeneous. What we're going to do is we're going to put in standard form first. So we've all seen standard form already. This is our standard form for a second order linear differential equation. And what we're going to say is that a particular solution for this differential equation, because remember, when we're solving the non-homogeneous, the key is we're looking to find the y sub p, the particular solution piece. The y sub c is the solution to the associated homogeneous. And now that we're solving the non-homogeneous, we need that y sub p piece. So what variation parameter says is that if we're trying to do this for, say, a second order linear differential equation, that particular solution can be of the form u1 y1 plus u2 y2, where y1 and y2 are solutions to the associated homogeneous, okay? And u1 and u2 are these functions of x that really we need to find. So ultimately, what we're saying is we know what y sub p should look like, okay? And we know two pieces of y sub p already because we would have found them when we solved the associated homogeneous. Ultimately, what we need to find is u1 and u2. And if we can find u1 and u2, then we can find the particular solution. So it takes this tactic of, we saw what happens with first orders, let's try and translate that over to second orders. All right. Well, if y sub 1 and y sub 2 solve the associated homogeneous, then when I plug them in to the standard form homogeneous, which is this, they should satisfy it. So that means when y1 prime, y1 double prime gets plugged in, it should equal 0. And when y2, y2 prime, y2 double prime gets plugged into the, again, standard form, it should equal 0 as well. So, these are basically just consequences of y1 and y2 solving the associated homogeneous differential equation. All right. Next, what we're going to do is we're going to impose an assumption, and that assumption is right here. What it really is a restriction. Okay, a restriction on what U1 and U2 can be. Now, there's no real good reason why we have this assumption or this restriction, other than because it works. Think about this. We could solve this, try and solve this with no restrictions put whatsoever on U1 and U2. But the problem with doing that is we get caught up in the computation when that starts to happen. And so when we get caught up in the computation, it starts to become to the point where we're not going to be able to work with this method. So if we go through this process and we get to a certain point where we go, well, if this piece were just 0, then we would be able to move forward. That's where this assumption essentially comes in. And it says, okay, we're going to make this assumption. We're going to make this restriction on U1 and U2. And we can make any restriction we want. We can just come up with any restriction. U1 and U2 have to be positive functions. Like that could be some random restriction we make. Does it help? Well, it depends on how this whole process works out. Well, while we're going through this process, if we make this particular restriction on U1 and U2, then it actually will help us simplify the derivatives of y sub p, and therefore help us solve using variation parameters. So there's no real rules on the restrictions that you can place on a method of solving, as long as those restrictions yield results. Now, you don't want your restriction to be too restrictive, because then you will have a hard time finding solutions that will satisfy all those restrictions. But there's really no good reason other than because this works, is that we make this assumption. All right, so we make that assumption. We have a setup of what our y sub p should look like. We know y1 and y2 solve the homogeneous. So then we go, okay, well, if this is what y sub p should look like, then that means when I plug it in to the differential equation, it should satisfy it. Well, in order to plug it in, I got to take the derivative of y sub p, I got to take the second derivative of y sub p, and you could see, well, that's going to start getting complicated because these are products here, and therefore I'm going to need product rule to do the derivative and then the second derivative. So let's take a look at that real quick. So y sub p prime, okay, we would have to do the product rule, so u1 y1 prime plus y1 u1 prime. And I'm dropping off the of x's because, you know, these are all functions of x. Then u2 y2 prime plus u2 plus y2 u2 prime. So again, just product rule. You know, this is product rule here for this first piece, and this is product rule here for the second piece. Okay. So then, if we said, all right, now let's take the second derivative, that's a lot to take the second derivative of. We'd have 4 product rules. However, if we impose this restriction right here, that y1 u1 prime, which is this one, plus y2 u2 prime, which is this one, equals 0, then we could say just, well, y sub p prime is just those two pieces, so it's just this. Okay, so then we're going to do the second derivative. And since we only have to take the second derivative of this piece, it's again 2 more product rules. So we get u1 y1 double prime, y1 prime u1 prime, u2 y2 prime, u2 prime y2 prime. And it's a lot, but really just product rule over and over again. All right, so now what we're going to do is we're going to substitute these in. We're going to take y sub p prime, and we're going to plug it in here for y prime. We're going to take y sub p double prime, we're going to plug it in here, and y sub p itself is going to go in here. And so when we plug those things in to this differential equation and then group out some terms, we get here. Okay? And so what happens is we get to the point where we can pull out a u1 out of a whole group of pieces, and that's going to get to here. We can pull out a u2 out of a whole group of pieces, that's going to give us here. And then here, this is what's left over. All right. Well, look at what happens. If we pull out the u1 piece, let me erase some of this, okay? If we pull out the u1 piece, this is what's left inside, okay? And what that is exactly this. And that should equal 0. And the same thing happens over here. When I pull the U2 piece out of this, I'm left with this Y2 piece. That's exactly this part. Again, that should equal 0. Well, if that zeroes out and that zeroes out, then this is really all I have when I plug it in. So we're left with this right here. All right. So now looking at what we have this piece right here. Again, we were ultimately trying to find U1 and U2. So we have this piece right here when I plug the y sub p into the original differential equation, saying, well, if this is a solution, then when I plug it in, it should work. And I get to this point. I also have my original assumption that we've been working with, that restriction here. Notice both of them have U1 and U2 prime in them. So what we can think of this as a system of equations. A system of equations where it has the variables U1 prime and U2 prime. Notice what else it has in it. What else it has in it is Y1 and Y2, Y1 prime and Y2 prime, which remember would be known already. Y1 and Y2, as well as Y1 and Y2 prime, will be known because they are solutions to the associated homogeneous, which we would have already had to have solved before we even try and move on to the non-homogeneous. So, of these two equations, there's two equations and really two unknowns, U1 prime and U2 prime. So if we think of this, okay, here's a system of equations where you have two equations and two unknowns. Let's solve that system for those unknowns. Now, if we could figure out what U1 prime equals and U2 prime equals, that could then help us figure out what U1 and U2 equal. So we need to solve this system of equations for these two variables. And then once we do that, we can find what we ultimately wanted, which was U1 and U2. So here's where the linear algebra comes in. Cramer's rule. Cramer's rule is a way of solving a system of equations where you have a certain amount of unknowns and a certain amount of equations. And one thing you always have to do when it comes to Cramer's rule is that the number of unknowns has to equal the number of equations that you have. So we have two unknowns and we have two equations. So the way we set this up is we look at these equations, that system of equations that I just looked at, and we pull it apart. And so these are just formulas that come from, again, Cramer's rule. So what we do is we take the knowns, okay, remember we know Y1 and Y2, as well as Y1 prime and Y2 prime. We're going to take that, we're going to call that W, okay, and we're going to create a determinant of those values. Then what we're going to do is we're going to take a combination of and that's all the stuff that would be over on the left-hand side, okay? Again, remember, we have these two equations. The two equations were Y1 U1 prime plus Y2 U2 prime equals 0, and Y1 prime U1 prime plus Y2 prime U2 prime equals f of x. And so we look at this and we say, okay, well, we have this piece and this piece here. That's going to create our first determinant. Then what we do is we take this piece here and the Y2s here, okay, and we create our next determinant. And then finally, what we do is we take this piece and we take the Y1s and we create our last determinant. So we're going to call these W, W1, and W2. And this would go similar if you've never had linear algebra, because let's say you want to solve a system like 3x plus 5y equals 7 and 2x minus 8y equals 0. Let's say you're solving that system, very simple system of two linear equations, right? We would set this pattern up the same way. Like I said, the first determinant would be these here, okay? The next determinant would be these with this one, and the last determinant would be these with this one. right? So again, if you've had linear algebra before, you kind of know where this all comes from. You know why it works. Without having linear algebra, it's really not that big a deal. It's just a matter of looking at these pieces. All right, so we have W, W1, and W2. So if we look at those three determinants, let's look at the first determinant here. We take this times this minus this times this. So that's going to give me y1, y2 prime minus y2, y1 prime. And that's your W. Okay? Then you have W1. W1 would be this times this, which would give me 0 minus this times this. So we're just left with minus y2 f of x. Okay? And then W2, same idea, this times this minus this times this. So the second one is 0, so we just get y1 f of x. And what Cramer's rule says is that we could find u1 prime, which is one of the variables, one of the unknowns we're looking for, by doing w1 divided by w, in which case we do this divided by this. So I'll just write as minus y2 f of x over w representing this piece. And then u2 prime is w2 over w, which again is y1 over y1 f of x over w. And so if we shorten this out here, what do we have? We have u1 prime equals negative y2 f of x over y1 y2 prime minus y2 y1 prime. And there's a formula for solving for u1 prime. And then we have u2 prime equals y1 f of x over y1 y2 prime minus y2 y1 prime. Again, there's a formula for u2, okay? Which, if you notice in this formula, what does it need to solve for u1 and u2 prime? Well, it needs f of x, which you would know because that just comes from the original function being put in standard form, key standard form. And then you just need y1 and y2 along with their derivatives. Well, those would all be known already as well because they would be solutions to the homogeneous. So you can find u1 prime and u2 prime using a bunch of things you would already know before you started this whole process. Once you find u1 and u2 prime, remember, we want to know what u1 and u2 are. Well, that's very simple. If we know u1 prime, u1 is the integral of u1 prime. And if we know u2 prime, u2 is the integral of that. So we find u1 and u2 by integrating. Once we have u1 and u2, then we create our y sub p. If this sounds like this is a big deal and this is going to take a little while, it is. Okay, this is not a short process, but you get better at it. And one thing you want to do is you want to get these two formulas committed to memory. Like, these are the ways we're going to do it. We're not going to go through this whole process of determinants and finding it, but really, I mean, these are determinants. But rather than set up the determinants, then calculate them, then put them into this formula, what we're going to do is just jump straight to these formulas. So you want to get yourself acquainted with these two formulas for u2 and u1 prime. But once we have those, we have our y sub p. Now remember, once we have our y sub p, then we have our general solution to the non-homogeneous, which is y sub c plus y sub p. All right, so here we go. We want to solve this. Now, notice it's a non-homogeneous linear differential equation with constant coefficients. It's a lot going on there, but this side's got constant coefficients, okay? It's non-homogeneous, and the whole thing's linear. We could use the undetermined coefficients, the annihilator approach for this one, because this function right here is able to be annihilated. And we could do everything we've done previously. However, we could also apply variation of parameters to this differential equation, which we're going to do because we want to get practice in doing that. So first thing we're going to do, first step, is you want to find y sub c, okay? And so that means we're going to solve the associated homogeneous. So y double prime minus 4y minus 4y prime plus 4y equals 0. So the auxiliary equation is m squared minus 4m plus 4 equals 0, of which we're going to factor that, so that's going to be m minus 2 times m minus 2, in which case you just get m equals 2, but that's repeated twice, okay, so it's got multiplicity of 2. So it's a repeated real solution, therefore our y sub c is going to be c1 e to the 2x plus c2 x e to the 2x. Great. So we have our y1 and we have our y2 to be e to the 2x and x e to the 2x. All right. We're going to need that. We need y1 and y2. But this right here is pretty important because that's half of the solution we're trying to find for the non-homogeneous, right? Y sub c. So remember, y equals y sub c plus y sub p. All right, so now that we have that, what are we going to need? We're going to need to do the second step, which is find y sub p. But the way we're going to find y sub p is we're going to say y sub p should be able to form u1 y1 plus u2 y2. Where we know that u1 prime should be equal to minus y2 f of x over y1 y2 prime minus y2 y1 prime. And u2 prime should be y1 f of x over the same denominator, y1 y2 prime minus y2 y1 prime. Okay. So in order to do this, we need y1 and y2, which we have here, but we also need y1 prime and y2 prime. So we might as well find those while we're here, and so that would give me 2e to the 2x, and here I would need product rule, so e to the 2x plus 2x e to the 2x. Then what we're going to need is we also are going to need f of x. Okay? Well, f of x comes from putting the original differential equation in standard form, which is making sure there's a 1 here, which there already is. So then therefore, the function on the other side, that's our f of x. And if you follow this all the way back to the beginning, that's the f of x we're talking about. So f of x is x plus 1 e to the 2x. All right, so we're going to take all this here, and we're going to need that in these formulas. Notice the denominator here. Remember, it's the determinant of the matrix y1, y2, y2, y1 prime, y2 prime, which is really just this minus this. So you don't really have to necessarily memorize the denominator, just memorize where it comes from. It comes from this times this minus this times this. Okay? And so that denominator in this case would be e to the 2x times e to the 2x plus 2x e to the 2x minus 2e to the 2x times x e to the 2x. And to simplify that a little bit, what I'm going to do is I'm going to say, all right, well, here's an e to the 2x I can factor out of this piece here and bring it out front with this one. And then here I have an e to the 2x, e to the 2x, and then this is going to have 2e to the 2x's that I can pull out. So I'm going to do all that, and what am I going to get? I'm going to get e to the 2x, another e to the 2x. I could add those exponents, but I'm not going to for right now. And what am I going to be left with? Well, if all that comes out, what I'm going to be left with here is there's going to be a 1 plus 2x, sorry, a 1 plus, 2x, okay, minus, then here's another 2x. So they'll cancel. So ultimately, this whole thing just turns into e to the 2x times e to the 2x. So that's the denominator down here in each of these. So keep that in mind. So then all we need is the numerator, and then we got our u1 and u2 prime. Right, just so we rewrite it, remember y1 was e to the 2x, y2 was x e to the 2x, f of x was x plus 1, or was it x plus 1 e to the 2x, and then that denominator we said was that e to the, this is the w, was e to the 2x, e to the 2x. All right, so u1 prime is going to be minus y2 f of x over w, which we said is e to the 2x, e to the 2x. Well, that's going to give me minus x e to the 2x times f of x, which is x plus 1 e to the 2x, over e to the 2x, e to the 2x. And you see, all right, well, cancel, 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 cancel. And so what do I end up with? I end up with x times x plus 1 with a negative, so minus x squared minus x. So that's my u1 prime. Well, if that's u1 prime, u1 is easy to find because it's the integral of u1 prime, so it should be the integral of negative x squared minus x dx, which in this case is going to be negative x cubed over 3 minus x squared over 2. And I'm not going to do a plus c because that'll come into play later. All right, then we go u2 prime, which was y1 f of x over the same denominator, e to the 2x, e to the 2x. Well, y1 is e to the 2x, f of x is x plus 1, e to the 2x. I have e to the 2x, e to the 2x, and you see again, cancel, 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 cancel. So we get x plus 1. Again, if that's u1 prime, or u2 prime, then u2 is just going to be the integral of x plus 1 dx, which is real easy to find. So then we get u2 to be x squared over 2 plus x. Okay? All right. So now that we have our u1 and u2, we find our y sub p. So y sub p is u1 y1 plus u2 y2. In this case, u1 minus x cubed over 3 minus x squared over 2 times y1, which is e to the 2x, plus x squared over 2 plus x times x e to the 2x. And so there's your y sub p. Now, we could do better than this. That's a big y sub p. It looks kind of messy. I could distribute this in here, distribute this in here. We're going to collect a lot of this because we're going to get a negative x cubed over 3 e to the 2x minus x squared over 2 e to the 2x. But then when this multiplies in, we're going to get another x cubed over 2 e to the 2x and an x squared e to the 2x. So we're going to have some like terms here and here that can come together here and here. So we put all that together, and finally, what do we get? We get y sub p to be, what does y sub p end up being? Y sub p ends up being x cubed over 6 e to the 2x, and that's just this x cubed and this x cubed coming together, plus x squared over 2 e to the 2x, and again for the same reason, this x squared and this x squared, giving you that. So now we got y sub p. All right, great. Let's finally solve the non-homogeneous. Well, the solution to the non-homogeneous is y sub c plus y sub p. So that's the full general solution. So that would be y equals, let's see if I have enough room to fit this in, c1 e to the 2x plus c2 x e to the 2x plus x cubed over 6 e to the 2x plus x squared over 2 e to the 2x. And that whole thing would solve the original non-homogeneous linear differential equation. So that's the variation parameters way of doing it. Now, it's integration heavy at one point with the u1 and u2 prime need to be integrated, but that wasn't too hard to do. We were able to integrate them fairly easily. We could have done this whole problem using the undetermined coefficients. I would have got the job done. I'm just showing you there's another way to do it. Now, the nice thing about this variation of parameters is it doesn't have all the requirements that the undetermined coefficients did. To apply undetermined coefficients with the annihilator method, you need a non-homogeneous linear differential equation with constant coefficients, and the function on the right-hand side has to be able to be annihilated. That's a lot of requirements. Variation parameters, we don't need any of that. We just need a non-homogeneous linear differential equation. Doesn't have to have constant coefficients, although right now they're all going to, because that's the only one we know how to solve. That will change next time. Next class we'll learn a new one. The function could be annihilated, doesn't have to be able to be annihilated. In this case it could have, but didn't have to be. This is the function. So variation parameters is much more widely used. It's able to be used for more problems. So there's a benefit in that. The downfall is that it could get pretty messy when it comes to the integration that we need to do. Right now, didn't for this problem, but it could. Let's look at another one. All right, now let's look at this one. Non-homogeneous, linear, constant coefficients, all that stuff that we've had in the last one, but now look at the function over here. Cosecant 3x. There's no way we're going to annihilate that function, so that annihilator method isn't even on the table at this point. So the only thing we can do here is variation parameters. So first thing we're going to do is find y sub c, okay? And so we're going to solve the associated homogeneous 4y double prime plus 36y equals 0. That means our auxiliary is going to be 4m squared plus 36 equals 0, giving us m equals plus and minus 3i, because we'll get a negative 9. We move the 36, divide by the 4, we get a negative 9, and so square root of negative 9 is going to give us plus or minus 3i. So in this case, we got a beta of 3, an alpha of 0. If that's the case, then our y sub c is going to be c1 cosine 3x plus c2 sine 3x. Again, because the alpha is 0. So there's your y sub c. So our y1 is cosine 3x. Our y2 is sine 3x. Now, it really doesn't matter which one you call y1 and y2. They're two solutions. So you could have said y1 was sine 3x, y2 is cosine 3x. It doesn't matter. As long as you're consistent through the rest of the problem of which one you called y1 and y2, then you'll still be fine at the end. So let's go y1 prime. We're going to need this, so let's just find it now. So it's going to be minus 3 sine 3x. And y2 prime is 3 cosine 3x. And we also need to know what f of x is. Now, f of x is not cosine 3x. F of x is what happens when we put this in standard form first and then look at the right-hand side. So this 4 has to divide over. So f of x is cosecant 3x over 4. So these are all the pieces that we need to find u1 and u2 prime. So let's go with u1 prime first. So our second step is to find y sub p, which is u1 y1 plus u2 y2. So u1 prime is going to be minus y2 f of x over y1 y2 prime minus y2 y1 prime. In this case, that would give me minus y2, which is sine 3x, times f of x, which is cosecant 3x over 4, all over this times this minus this times this. Okay? So in this case, we're going to get a 3 cosine squared 3x minus this times this. Since there's a negative here, this becomes a plus 3 sine squared 3x which if you factor out the 3, you get cosine squared 3x plus sine squared 3x, which you know is going to be 1. So ultimately, this whole denominator down here is just going to be 3. Okay, so let's go a little bit further to simplify this, because we're going to have to integrate it. I don't want to leave it as is, so what are we going to have here? We have this 4 here, we have this 3 down here, so it's going to come out as a 1/12. We have a minus sine 3x, and then we have cosecant. Well, cosecant is 1 over the sine. So they're going to cancel. So ultimately what I get is negative 1/12. Well, if that's negative 1/12, then that means u1 is the integral of negative 1/12, which is negative 1/12 x. So there's my u1. Then we move on to u2. Remember, u2 prime, the formula is y1 f of x over the same denominator. We found out the denominator is just going to turn out to be 3, so I'll just jump to 3. So in which case we're going to get cosine 3x times cosecant, which I'm just going to jump straight to 1 over the sine. I also have this 4 down there as well, and then this is over 3. So we get 1/12, and then we're going to get cosine 3x over sine 3x, which we could leave as that, or we could write it as 1/12 times the cotangent of 3x. So it depends on which way you want to do it, because we're going to have to integrate one of them. Do you want to leave it like this and integrate this one, in which case you're going to do a u and then a du, or do you want to leave it like this and remember what the integral of cotangent is? Either way, you should be able to handle it, but we're going to have to integrate that to find what u2 equals. So u2 is going to be the integral of, what did we say? We said 1/12 cotangent 3x dx. And so you should know how to do that integral. So that's going to be, 1/12 is going to come out. So I'm going to get the integral of cotangent is log of the sine. So log of the sine of 3x. And then it's going to be over 3 because of the 3x. So I'm going to end up with 1 over 36 log of the sine of 3x. And then we go and say, all right, let's find our y sub p, which in this case is going to be u1 y1 plus u2 y2. For us, that would be the minus 1/12 x times cosine 3x plus 1/36 log of the sine of 3x times the sine of 3x. Okay? And there's not really much I could do to simplify that. I guess I could pull out a 1/12, but that doesn't do much to help us. So we're just going to leave y sub p as that. So then our general solution is y sub c plus y sub p. In this case, it's c1 cosine 3x plus c2 sine 3x minus 1/12 x cosine 3x plus 1 over 36 sine 3x. I like to put this up in the front here so it doesn't get embedded inside this log, because this is separate from this. So then we get log of the sine of 3x. Okay? And that whole thing is the solution to the original differential equation. But this one had to have been done by variation parameters. Really didn't have a choice. That undetermined coefficients was not an option for this example. On this last example, there's something that happens here with this one that needs to be addressed. It's not the greatest example, but the fact that something that occurs in this one needs to be talked about is the reason why we give this. So, again, looking at it, it's a linear non-homogeneous, constant coefficients on the left-hand side. Here's a function we can annihilate. So this variation of parameters is really our only bet to get this thing done. And if we do it, we follow the steps again. So the first step is y sub c. So y double prime minus y equals 0. In which case you're going to get m squared minus 1 equals 0. So m equals plus or minus 1. Right. So that's going to say that y sub c equals e to the x, or I forgot c's, c1 e to the x plus c2 e to the negative x. Pretty simple, no big deal, that's done. So our first solution is e to the x, our second solution is e to the negative x. So then y1 prime is e to the x, and y2 prime is negative e to the negative x. And we also need to know what f of x is, in this case 1 over x. This has to be put in standard form, it already is, so there's your f of x. So then here's the problem. The second part is to find y sub p, which is u1 y1 plus u2 y2, where u1 is minus y2 f of x over this y1 y2 prime minus y2 y1 prime. And this isn't too bad, so minus y2 is minus e to the negative x, f of x is 1 over x. To find the denominator, we do this times this, minus this times this. So we're going to get, what do we get here? We're going to get a e to the x times an e to the minus x. Well, they're going to cancel each other out, because e to the minus x, remember, is 1 over e to the x. And so we're just going to get a negative 1 there, minus this times this. Well, same thing's going to happen here. So minus another 1, so we end up with negative 2 in the denominator here. So ultimately our u1 prime is 1/2 negative e to the negative x over x. And that's what we have to integrate. There's our problem. If I want to find u1, if I want to find u1, I have to do the integral of 1/2, let's say negative 1/2 e to the negative x over x dx. The problem is that's not an easy integral, in that we don't really have a way to do that integral. You haven't learned a way of integrating something like this ever in all your calc experience, which happens, right? Some integrals, they just can't be done. They're not some elementary function that we've learned before. So in which case, this is the best we can do for u1. And what happens is, unfortunately, the same thing also occurs in u2. If I look at u2 prime, it's y1 times f of x over the same denominator, so minus 2. So we end up with this, minus 1/2 e to the x over x. And then u2 is going to be the integral of minus 1/2 e to the x over x. And I know we look at this and you might say, oh, integration by parts is the way to go. But integration by parts doesn't work because we're dividing by the x. If it was x e to the x, yes. But no, not in this case. So again, not really an integral we can do for elementary functions that we've worked with. And so in this case, this is u1 and this is u2, and that's the best we can do here. And sometimes we have to leave it like that. Now, that being said, on a test, I would never give you something like this, because you wouldn't know you can or can't do it. You would just think, I can't figure this out, I'm doing something wrong. So I won't give you something like this on the test where you can't do the integral for u1 and u2. All the u1 and u2s will be integrals you can do for the functions you have worked with in the past. So this won't necessarily happen to you on a test, but it could happen in the real world. All right. So once we have our U1 and U2, and you say, okay, well, that's the best we can do with those, we can still form our solution. So we say our y sub p is u1 y1 plus u2 y2, in which case u1 and u2 are just integrals, okay? So we're going to have the integral of, what was it again? It was the 1/2 e to the minus x over x, and it's the integral of that, okay? And that's going to be multiplied by e to the x, okay? So this is dx, okay? Plus u2 was that other integral of, what was it, minus 1/2, minus 1/2 e to the x over x dx, and that was times e to the negative x, because that was y2. And so, okay, well, there's y sub p, and then the general solution should be y sub c plus y sub p, so it should be c1 e to the x plus c2 e to the negative x plus, and then we could just do all this all over again. I'd probably put this e to the x on the outside and do the integral of 1/2. I could probably pull the 1/2 all the way out as well. E to the negative x over x dx, minus 1/2 e to the negative x times the integral of e to the x over x dx. And I'm just rearranging these terms here. But nonetheless, okay, there's your whole answer. It doesn't look great. There's integrals in the answer, but it is a solution to differential equation. I mean, we would have to figure out what this is, and at this point, you would use computer software to try and find those, because they're not elementary functions. They're not just simple functions we could take care of with things we've learned to this point. But we do have a solution to the differential equation. Not ideal, but again, can be done. So this can happen. This will not happen on a test, but this can happen, which is the reason why we introduced this example. All right. Now, variation parameters can be applied to higher order differential equations. So third, fourth, fifth order non-homogeneous differential equations. It just requires you to be able to apply Cramer's rule to higher sets of unknowns, which instead of 2x2 determinants, we would actually need 3x3 determinants or 4x4 determinants, and it starts to get pretty rough. But it can be done. So the idea is we follow a lot of the same tactics. First off, we put our higher order one in standard form. Okay? The key is so that we could find this f of x on the other side. We find the general solution to the homogeneous. So we would have a certain number of solutions there, depending on how big it is. So 2, 3, 4, 5 solutions to the associated homogeneous. Once we have the y1, y2, y3 up to whatever, we look at what the form of y sub p would be, which would be u1, y1, u2, y2, then u3, y3, all the way up to un, yn. So we would just have to find all those u's. So we'd have to find u1, u2, u3, u4, u5, etc. Well, in order to do that, what we're actually going to do is find u1 prime, u2 prime, u3 prime. We're going to create a series of equations, okay, that are going to be our sort of constraint equations like we did before, and that would come out from looking at the derivatives and how to simplify those derivatives. When we plug all that in to the original differential equation, we're going to be left with a particular equation at the end, okay, which would be another equation that has u1 prime and u2 prime and u3 prime, etc., equals f of x. Here's our system of equations, all of which have the same set of unknowns, u1 prime, u2 prime, u3 prime, u4 prime, un prime. We would have to solve for those unknowns using Cramer's rule, which Cramer's rule works for as long as you have the same number of equations as you have unknowns, and that's what's going to happen here. We would have 3 unknowns, 3 equations, 4 unknowns, 4 equations. We can use this Cramer's rule formula to solve for u1 prime, u2 prime, u3 prime, etc. And we could solve it. Now the problem is, though, when you have this bigger set of equations, these pieces of Cramer's rule, these wk's and w's, are determinants, and they would be 3 by 3 determinants or even 4 by 4 determinants, which are extremely difficult to find when it gets to a certain point, and we have to find multiples of them in the process before we even start integrating. And so, yes, this can be done for higher order differential equations. No, we will not be doing it. We will stick to second order variation parameters equations. Couple reasons. One, we don't necessarily have a strong background in linear algebra right now for everybody, so I don't really want to get into that. Two, the problems are just done the same way. It's just a lot of time to get them done. So if you can do second order, you technically can do third, fourth, fifth order if you just have enough time on your hands and have the background knowledge that you need from Cramer's rule in linear algebra. So, yes, it can be done, but no, we won't do it. So we'll stick to variation parameters with second order differential equations. Eventually, we're going to kick it up to ones that don't have constant coefficients. So that's the next lesson. I was looking at a different type of differential equation that has coefficients that aren't constants, but we already know the method of solving the non-homogeneous by having variation parameters in our back pocket to use. So, the variation parameters is an extremely effective way of solving these non-homogeneous linear differential equations. Because when we use this in the solving process, we don't put a ton of restrictions on what kind of differential equation we have, other than it's linear and it's non-homogeneous. But other than that, the coefficients of the linear, these coefficients that we could work with, can be anything, which is really nice.